Okay, guys, so in 10.3, we're going to talk about polar coordinates. In this video, we're going to do a little bit of review of polar coordinates, then we're going to look at some graphs and how to enter it in our calculator. Then once we're done with that, the next video on 10.4 will be about doing calculus with polar coordinates. So 10.4 is going to be the much harder section. 10.3, we're going to kind of do it light, kind of talk about some graphs, things like that. Okay, so first, review of polar coordinates. Say we have this point, let's call it x comma y. Well, polar coordinates can describe it similarly by telling you how far from the origin is, that's our radius, and then by telling you the angle that it took to get there, to take that radius at. So, and again, this is considered the pole, that's why it's called polar coordinates. And you can do a lot of cool shapes with polar coordinates, non-functional shapes. So that's what we're going to kind of go over today. We have a few rules for polar coordinates. Polar coordinates use, instead of x and y, polar coordinates use polar coordinates use r comma theta. Well, I do not think that is the correct spelling, but we'll come back to that. So there's a few things that you guys hopefully remember from your previous class, your pre-calc class, is that if you were going polar to Cartesian, so polar to Cartesian, or if you go from Cartesian to polar, okay? So if you want to convert polar coordinates to Cartesian coordinates, or if you want to convert Cartesian coordinates to polar coordinates, these are the formulas you could use, and they make sense. X equals r cosine theta, and y equals r sine theta. And then if you're trying to go from Cartesian to polar, you do x squared plus y squared equals r squared, so that's a circle. And we have y over x equals tan theta. So these are formulas that you learned in your pre-calc class. And again, these right here are actually pretty convenient because we have, if you think about it, they came from x over r equals cosine theta and y over r equals sine theta. Literally, all we do is we multiply r to the other side and we have that, okay? So really quick, let's just do a few problems. So it says, write 2 comma negative 2 root 3 in polar coordinates. There we go. Coordinates. Yeah, I don't know why I wrote it that way. Oh, the notes that I use. Okay, have it wrong, but that's okay. Coordinates. Okay. So write 2 comma negative 2 square root of 3 in polar coordinates. So right now it's written in XY coordinates. So the first thing you guys should do in general is you should always kind of graph where you think this point would be at. You would estimate it, okay? So I would estimate it to be, if we go over 2, that's here, and then we go down 2 square roots of 3, that's right about here. So we think that our point is right about there, 2 comma negative 2 square roots of 3. Okay, so that's right about where we're at. So we should end up in quadrant 4, all right? So we're gonna look at our little rules here, and it says Cartesian to polar, okay? So Cartesian to polar. Well, then it says to use x squared plus y squared equals r squared. Okay, so, well, let's plug in what we know. We know that x is 2, so this is 2 squared plus negative 2 root 3 squared is equal to r squared. So then we have 4 plus 4 times 3 is r squared. So then this will be, what, 4 plus 12, so we get 16 equals r squared, and r is equal to 4, okay? So we got our radius of 4. Oops, what happened there? So now it says we need to use y over x is equal to tan theta. So we got to find the tangent of theta. So that means we got to find theta. Well, we know y is -2 root 3, and then we know x is 2. So this is really -√3 equals tan theta. So then you think of your unit circle. When would the -√3 equal tan of theta? So you could do arctan to both sides, or you could just try to think, well, √3/2, it's either a 30 or a 60-degree triangle, 60-degree angle. So we could just do second arctan of negative second function √3. And I'll put it in mode. Let's go degrees real quick. So I get -1.047 mode. Let's go degree. And I get -60 degrees, which makes sense because look where I'm at. That would be -60 degrees or -π/3. In general, you should probably use -π/3. So we're going to say then that theta is worth -π/3. Okay, so we now have our coordinate. We have 4, comma, -π/3. Okay, now here's the thing. There's another way that we could write this exact same problem, right? Think of our unit circle, right? If we're here, or I guess don't think of it as a unit circle, but if we're here, right, we're here, that technically was -π/3, but couldn't I also do the same exact problem and go around 5π/3? So I could have also used 4, comma, I'm sorry, not 4π/3, 5π/3, right? That would have given me the same answer. Or we could have done something even weirder where you can actually use a negative radius, okay, to describe it. So all a negative radius does is it reflects it 180 degrees, reflects it across the origin, basically. Well, not across the origin, but across over 180 degrees. So I could have said -4, let's do this with a negative radius, -4, comma, and then let's go 2π/3. So let's see. If we go 2π/3, 2π/3 is right here, right? That would read right there, and that would be with a radius of 4. So this value right here would be 4, comma, 2π/3. So if I do 180 to it, that would come over here, and this would be -4, comma, 2π/3. So the negative radius can transfer it over 180 degrees, okay? So that's another way you could write it. So all three of these would be correct answers, okay? Those would all be correct answers for this problem, okay? So now let's go the other way. Let's just do a little practice with, so let's say, let's write 4, comma, π/4 in Cartesian, okay? So I'm going to first, oh, and by the way, you guys, it's really important that you graph. So always graph your point first. It's really important because it'll help remind you what quadrant you're supposed to end up in. So when I get that -π/3 as my answer, it made sense to me because I knew I was supposed to end up in quadrant 4. It basically prevents you from making silly mistakes. So make sure you do that, okay? So now we want to write this in Cartesian. So we're going to go up and we're going to look over here, and it says to write polar to Cartesian, x is equal to r cosine theta and y is equal to r sine theta. And these should make sense to you because in general, x is associated with cosine, y is associated with sine. Okay, so the first thing we're going to do is we're going to say that x comma y, we know that this is equal to r cosine theta comma r sine theta. Well, that's pretty straightforward because we know that the cosine of theta or we know that r is 4, and then we know the cosine of pi over 4. We know how to do that. So that would be 4 times square root 2 over 2. So we get 2 square roots of 2, right? That seems pretty straightforward. Yeah. And then let's do y. Y is equal to 4 times the sine of pi over 4. And this time we would get 4 times square root 2 over 2, which is 2 square roots of 2, right? So we actually have our point, 2 square roots of 2, comma, 2 square roots of 2. Sounds good to me. No big deal, right? So to me, in general, it feels easier to convert to Cartesian. Taking a Cartesian coordinate and converting it to polar seems a little bit more difficult to me. But this is just a little bit of a review that you guys had in your, or from your pre-calc class. So I want to move on. I don't want to spend too much time on that, but there will be some homework problems for you to practice doing that. And if you have any trouble with it, please let me know. So what I'd like to do is kind of demonstrate something to you guys about why we're going to use our calculator to graph Cartesian so heavily, okay? So, I'm sorry, to graph polar coordinates so heavily. So it says graph r equals cosine of 2 theta. Okay, so what I'm going to do is I'm going to graph using polar, and that means I need to know my theta and I need to know my r, right? So I'm going to plot some points, and I'm going to pick ones that I kind of know pretty good. I'm going to pick 0, we'll go with pi 6, we'll go with pi fourths, we'll go with, what's another good one? Pi thirds. What's another good one? Pi halves, I guess we could go with. And we could even go 2 pi thirds if you want. And we could just keep going. Okay, but I'll just stop there. Okay, now my radius is the cosine of 2 times whatever theta is. Okay, well, what theta is in this first part is 0, so the cosine of 0 is 1. When we plug pi 6 in, we get cosine of pi thirds, and that would be 1/2. Cosine of, what would that be? Pi halves would be 0. And then I'll just fill the chart in for you guys here. -1, -1/2. So now, if I try to go and graph this, this is going to be a little bit difficult, okay? Because I got to go over 0 and a radius of 1. So that's going to be tough in and of itself. Okay, so we're going to go over 0, radius of 1. That one I can put right there. Let me put it in red. Okay, so I'm going to eyeball that as 1. Now here's where it gets, that wasn't the tough one. The next one is pi 6. So pi 6 and then 1/2. I feel like maybe this is 1/2 right here, and I feel like pi 6 would be there. Okay, and then we got pi fourths is 0. So pi fourths would be right here, and we have a radius of 0. And then we're going to go pi thirds. So that's like here somewhere, right? Pi thirds. And we go down 1/2. So pi thirds, comma, -1/2. Remember, it should have been here, but we now have to reflect it over here. So I feel like it's going to be, I feel like it's going to be reflected like right here somewhere. I don't know. And then pi halves would be up here somewhere, right? That's pi halves, but then we go -1. So pi halves 1 would be here, so -1 would be here. And then we're going to go 2 pi thirds, -1/2. So 2 pi thirds would have been 1/2 would have been like right here, but because it's a negative, maybe I messed up on the pi thirds -1/2. Pi thirds -1/2 probably should have been right here somewhere, right? And then 2 pi thirds -1/2. So here's 2 pi thirds, right? That's 2 pi thirds. Okay, so then our -1/2 should be like right there. So let me see if I can connect the dots. Okay. Oops. Okay, so that's looking a little rough. around the edges there. Let me see if I can clean this up just a little bit better. So I think it's supposed to be like that. So what I'm going to do now is I'm going to get out my calculator and I'm going to switch the mode to radians, but I'm also going to switch to polar. Okay, and you could have done this for parametric E also, but I wanted you guys to learn to do it by hand. So now we're going to go to y equals, but when we go to y equals, we see that it says R1, R2, and R3 because now we're graphing in terms of the R's. Okay, so it says R equals cosine of 2 theta. So I'm going to do cosine of 2 theta, and I graph. And let me do my window from 0 to, let's go to 2 pi. Okay, and let's do that. Max is max min. Let's do -5. Let's do 5. So I'm just messing with my window right now. Okay, so let's graph. Yep, so this is what I get. I get this. So this is my drawing was supposed to be this, by the way, guys. It was supposed to be this little rose petal. In general, maybe I can draw it better. It's supposed to be like this, like this, like this. So in general, that's what we were supposed to get. But the practice of this, or the point of this exercise, is to show you that graphing polar by hand is really, really hard unless you have like a perfect sheet of polar graph paper, which, you know, would be like this. Maybe you guys have seen that before. We're not going to really go over that. We're going to focus more on the calculus part. So this first 10.3 is just about getting comfortable using your calculator and kind of identifying shapes. Okay, so let's look at some of these. Okay, circles. Okay, so circles have this form. R equals a cosine of theta. And these are circles tangent to the y-axis at the origin. Okay, so let's just do, okay, at the origin with a diameter of A. Okay, so if I gave you R equals, as an example, 2 cosine theta, you would just draw it and it would look something like this. Let's say that it's, so here's the 2, here's the 1. So it would be this circle like this. Okay, something like that. Okay, so that would be your circle. Now this would be R equals, let's do a different one, -2 cosine theta. And this would also be a circle. I guess I should have drawn it in red. Oh man, I butchered it. Okay, now if I did -2 cosine theta, well then it would be this guy over here. You get the idea, and this would be a 2, right? It has a diameter of 2. Okay, so let's move on. So let's take a note, the theta values between 0 and pi will give, oh my gosh, will give the entire circle. So take a minute, try to graph these on your calculator. Okay, so go into y equals and then do 2 cosine theta and just make sure that you can get a circle. It looks a little bit like an ellipse, but I think that's just your calculator screen might be on rectangular mode somehow still. But yes, it is a circle. Okay, so let's look at the next one. Now, as you guys could see, I'm not going to go, these are, I guess I got to write it, R equals a sine theta. These are circles tangent to the x-axis. X-axis at the origin. And you guessed it, with a diameter of A. So I'll just do one for you guys on this one. If we got R equals 2 sine theta, we would draw our little circle here, and it would look something like this. Sorry, I keep screwing up my circle. So, and would have a diameter of 2. Okay, so this one would be on the x-axis. Okay, so let's look at cardioids. So cardioids, limacons, limacons, and loops. Okay, so these are kind of, they all fit into a certain category, and it depends on, so these are polar graphs. They depend on the relationship between the A and the B that I'm going to write for you right now. So these are polar graphs of the form R equals A plus or minus B sine theta, and R equals A plus or minus B cosine theta. Okay, and they have different shapes based on the relationship between A and B. So the first one will be cardioid. Okay, cardioids is A equals B. Okay, so this would be an example, R equals 1 plus cosine theta. So when the A and the B are the same number, the number in front of the sine or the cosine is the same as the number that's off on the side, we get a different shape. So it kind of looks like this. Okay, that's what 1 plus cosine theta is. And I would graph this in your calculator on polar form just to give it a shot to make sure you can get it. The orientation, I'll write this in green. The orientation of the cardioids needs to be determined by plotting, good values that we're used to working with. Theta equals 0, pi halves, pi, plain old pi, and 3 pi halves. And that should give you a kind of a good setup of what you're getting yourself into. But again, you could just take out your calculator and graph it. So again, you guys all have a graphing calculator to take this course. So you shouldn't have too hard of a time noticing what you're getting yourself into. It's more important that you kind of say, okay, this is a shape I'm dealing with. This is how it behaves. But your calculator should give you a good picture of it, okay? So let's do a limacon now. Okay, so limacons have A greater than B. So a good example would be R equals 2 minus sine theta. Okay, I guess I could draw it over here. Oh no, that wouldn't work. So limacons, okay, so we can draw this here. And we have, I'll give you 2 minus sine theta. We can go up here to 1. I'll draw these guys in red and green. So there's like this little flat line right here. And then it comes out here to 2, and it comes out here to 2. and then it goes and it creates this shape. So this is all supposed to be curved, guys. I really butchered it on the edge, but hopefully you guys get the idea. And this will be -3. Yeah, sorry about that. Hopefully you guys get the idea behind it. It's supposed to be symmetric. That's the good thing about a lot of polar graphs, is everything really, there's a lot of symmetry with almost everything you're dealing with. So when it comes to calculus and integration, we're going to use this to our advantage quite often, okay? Let's look at another one. Let's look at the loops. And again, graph this in your calculator just so you can see that little flat line right there. Loops are A less than B. And these would, for me, these are kind of the harder variety, okay? Inner loops have something you may want to, and limacons, you could find the orientation using the same values, but inner loops are a little bit, there's a little more to them. Orientation. Use the same as above. 0 pi halves pi and 3 pi over 2. Same as above. Orientation. Basically just how it's going to set up. Use same. I could just write it out. 0 pi halves pi and 3 pi halves. Okay, but again, a lot of this kind of gets left by the wayside because we have our calculators to really help us with this. So we have r equals 1 plus 2 cosine theta. Let's look at this one. So this one would look like this. And now these are a little bit harder for me to draw. Well, all of them are really hard for me to draw, but okay, so it has this inner loop, okay? And the inner loop is kind of the important part when you're trying to do some calculus for these, okay? So basically what you have to do in order to find the inner loop when you enter the inner loop and when you exit the inner loop is, so note, the values of theta that produce. So again, you guys, you're basically, a lot of the problems you deal with, they want to know, you know, a section of the inner loop, or what's the graph, what's the area under the curve without the inner loop. There's all kinds of stuff, half of the inner loop. So a lot of the stuff you deal with these problems with integration will deal with the inner loop. So it says the values of theta that produce the inner loop, okay, lie between the solutions to r equals 0, okay? So this is very important for the calculus, for integration. So for us, for this problem, the inner loop, okay, so we say 1 plus 2 cosine theta is equal to r, but r is 0 in this case because we're going through the center, okay? So then that means cosine of theta is equal to -1/2, okay? So when would theta in our unit circle, when would theta have a cosine or an x value of -1/2? Okay, well that would be here, right? Because this is -1/2 comma square root 3/2, okay? And that would also be here as well, okay? And that would be what, 4 pi thirds? So this is 2 pi thirds, and this is 4 pi thirds. So that means our inner loop, so theta equals 2 pi thirds and 4 pi thirds. So that means our inner loop takes place 2 pi thirds less than theta, less than or equal to theta, is less than or equal to 4 pi thirds. And this is basically talking about when the inner loop starts and when the inner loop ends. Almost like you go into the loop, you walk around inside there, and then you come back out. These are the two values that would make that happen. Okay, so that's kind of important for the next section. It won't matter too much for this section, but it's very important for the next one. Okay, let's do one more. We have two types of roses. And then I think that'll be it. So roses let's say, roses have the form R equals a cosine n theta, and R equals a sine n theta. Okay, so let's look at R equals a cosine theta. So R equals a cosine theta first. Oops, n theta. Oh, man. Okay, so R equals cosine n theta. And there's a few things. If n is even, there are 2n petals. Okay, so the relationship of even and odd and the number of petals, okay. If n is odd, there are n petals. Okay. And again, this is the first loop. So technically roses have more than one loop, but if you want to think of it as, you know, the first one, that's kind of the general one, you know, it's kind of arbitrary, but the angular boundaries, so what the first loop is found in between, for the first loop, and again, depending on where you want to talk about it, it could be different places, but we kind of have our general first loop. Technically, if it's symmetric, then you could find any of the loops and they would all have the same area. Okay, so the first loop are given by negative pi over 2n less than or equal to theta less than or equal to pi over 2n. Okay, so this once again will help us in 10.4. It doesn't come into play too much in 10.3 just yet. Okay, so let's look at an example. So we have R equals 3 cosine 2 theta. So I'll just draw the rows. Okay, so you guys don't make fun of me. Oh my goodness. Okay, we'll do it in red. Okay, so we have this. Okay, I'm doing my best here, guys. I am not an artist. Oh man, it's already the worst. And then, okay, so we have our rows that's supposed to be symmetric, but I really butchered it. Okay, and you know, it's not a coincidence that this is a 3 and that's a 3, right? Now, there's 4 petals because remember, for this, if there is an even number in front of theta, then there is double that number of petals. So in this case, there's 4. If it were an odd, we would have, you know, whatever the odd was. If it was like a 3, we'd have 3 petals. And so when they're talking about these angular boundaries, we have to find those, okay? So it's negative pi over 2 times n less than or equal to theta less than or equal to pi over 2 times n. But in this problem, n is 2, so we end up with negative pi over 4 less than or equal to theta less than or equal to pi over 4. Okay, so what they're saying is, right here, we have this angular boundary, and we have this angle, right? And this is pi force, and this is negative pi force. And that first loop is in between here, right? That's how it was bounded, okay? So that's what they mean by angular boundaries when you see that problem, okay? Let's look at another one. So it says, so this one was for R equals a cosine of n theta. So now let's do R equals a sine of n theta. Okay, so this goes the same. If if n is even, there are 2n petals, and if n is odd, there are n petals. Okay. Now let's look here. The angular boundaries for sine are different. So the angular boundaries for sine, for the first loop, for the sine, a sine n theta, for the first loop are given by, and then we'll do 0 less than or equal to theta less than or equal to pi over n. Okay, so let's do r equals sine 3 theta. Okay, so angular boundaries. Okay, so angular boundaries would be 0 less than or equal to theta less than or equal to pi over n, which is pi thirds. Okay, so if we go to draw this, I'll take out my calculator and I'll type in r equals sine 3 theta, and I will get something like this. Okay, and then this angle here and this angle here, this angle right here should be the angular boundaries for this problem. So we got 0 to pi thirds. Okay, so that's how, I kind of drew this bad. Okay, so that's how they're bounded by these two boundaries of pi thirds and 0. Okay, so that's how, and you're going to use these when they ask you to integrate a rose petal. They're going to ask you to integrate and find the area of this rose petal from 0 to pi third. Now, what if they ask you to find the area of the whole rose petal? Well, you would still do 0 to pi thirds, but then you would just triple it because they're symmetric. So whatever area is in the first one, you'll find the same area in the next two. So you would just find the area of one and triple it. There's much worse. There's an example problem. I'm not going to do it. I can't draw it. It'll take me too long, but of 2 sine 4 theta. So you know, if you're doing 4 theta, how many petals are there? Well, there has to be 8 petals. Well, I guess I could try. So this is, oops, let me do it in red. It's going to end up looking terrible. So this would be 1, and then here would be the second. Yeah, that's already bad. And again, it's supposed to be symmetric. It's my drawing that's bad, you guys. Okay, it looks like a balloon animal, I'm sorry. So this one would have angular boundaries of 0 less than theta less than or equal to pi over 4. So that means right here, this first loop is contained within 0 and pi over 4. Okay, those would be our angular boundaries. So as you can see, we could definitely then go and try to integrate this, and we would sweep. We would do a sweeping motion to find that area, and that's how we're going to integrate it, okay? So this will be what we're working our way towards. The video is already going longer than I wanted. I think I'm going to go ahead and stop the video now. We'll go over tangent lines and derivatives in 10.4, even though it's kind of part of 10.3. I'll kind of piece it together for you guys, okay? So you may not be able to finish everything in 10.3 homework, but you should be fine, okay? All right, you guys, see you in the next class.